Hey, AP Chem. Today we're going to keep digging into Unit 6, our thermochemistry unit, and we're going to be taking a look at a lab technique called calorimetry. Now, you have heard us use the term or the unit joule for measuring heat, and I've also told you about how energy could be measured in calories as well. And if you think about kind of the root calor, even in Spanish, calor means hot or heat. So calor and then METR means to measure. So if we think about calorimetry, we are literally measuring heat, and that's exactly what it is. So calorimetry is a lab technique that's used to measure amounts of heat that are transferred to or from a substance. Now, this could be a chemical reaction. This could be an object that you put into a substance. And the general idea behind a calorimeter is that I need to use a substance that is able to be observable to help me measure the heat transfer from one object to another. So like there isn't like a little like radar, what am I talking about? A little like gun basically that you can point at an object and be like, there are 10,000 joules in that thing. There's no joulemometer, okay? So there isn't like an energy meter in terms of something where I can just like shine it on there and it will catch a transfer. So what we need to do is we need to basically, when we set up a calorimetry experiment, set up something that serves as a mirror that reflects the energy change that's actually happening in our process. So whether it's energy change coming from some sort of object that we put in there, like I said, or some sort of chemical process, we need something that is tangible and is measurable to show us what's going on in that process. And in our setups, we use what we call a calorimeter. And a calorimeter usually has one of two setups. Now, because we are a little on the lower end of the budget scale, our calorimeter is typically constructed with two styrofoam cups and a lid. So in this picture here, you can kind of see the styrofoam cups there, and then they have a lid on them. And then a lot of times there will either be a stirrer, which is like something you manually move, or you can actually put a stir bar in there and let it sit on a hot plate. You don't turn it on because it'll melt the cup, but you use the stirring portion of the hot plate on there. And then you have a thermometer. And then what's most important is that you have water in the calorimeter. And the water is what we are going to be using as our mirror to reflect our energy changes that are happening. So whether we put a chemical into the water or run a chemical reaction in the water or adjacent to the water is going to show us that change because the water is either going to provide energy to make that change happen in an endothermic process, or if it's an exothermic process, it's going to absorb the energy from that process that we have. And if we stick an object in there, if the object is hot, it will transfer its heat out into the colder water. And if it's cold, the water will transfer its energy into that object. And what's nice is we can use the change in temperature of the water to show us what's going on in that other thing. And I'll get into the math a little bit later, but that's generally the idea behind it. One of the reasons why water is really nice too, and we've talked about this before, water has a high specific heat, so you can get a big change in energy happening for an object or a chemical reaction, but it's not necessarily going to cause a huge change in energy for your water, and so it'll stay in its water liquid form inside the calorimeter. So that's what we typically use in class. Now, if you're fancier, which we are not, but like if they are trying to analyze, let's say, like energy in a food or something like that, they would use a fancier calorimeter called a bomb calorimeter. And it's not like, it's going to explode. What they do is they call the little container where they run the reaction the bomb. So what happens is they have an insulated container that's a little fancier than your styrofoam, and then they fill it with water, and they have a stirrer to keep the water moving around in there, just like we had in our previous setup. And then there's a thermometer to measure the energy change for the water. But then in a bomb calorimeter, what they will do is they will usually combust a piece of food, a small sample of it in there, and then they will measure how much energy goes from the bomb out into the area around it. And that's how they'll calculate like energy changes in like food and stuff like that. So they figure out how many calories something has. So that is the general gist about the calorimeters. Now, fundamentally, they work off the idea that the amount of heat that is leaving one object in the calorimeter has to be equal in its magnitude, but opposite in its sign. And so what we say is that positive Q equals negative Q. So the heat that is absorbed by one thing is equal to the heat that is lost by that other thing. And we're assuming that our calorimeter isn't losing any heat in these circumstances. They certainly do absorb a little bit of heat, but you are not going to be required to compensate for that in the calculations. So when we talk about calorimetry questions, the most complicated thing you're going to see is a question where they give you data for what is going on in one thing and the other thing. And you need to set those two things equal to each other. But the general gist, if you think about MC delta T as our Q equation, is that the energy that one thing is taking in has to be equal but opposite in sign from the energy that the other object or reaction or whatever is losing. And like I said, our water is always going to be the mirror for that situation. Now, I feel personally like the easiest way is for me to show you what I'm talking about by doing an example. So that is what we're going to take a look at in just a minute. So the example that we're going to be taking a look at is a sample of metal that we are going to be putting into a calorimeter. So typically what you do is you take either a cylinder of metal or like an actual physical sample of it. You'd weigh this out, and then with metals, because they heat up so easily, we would throw this into something like boiling water where we know the temperature of the boiling water. Then you put in a specific measured amount of water into your calorimeter. Most of the time people use increments of like 50. So they put in 50, 100, 150 milliliters of water in here. And then you take that piece of water or that piece of metal and you throw it into the calorimeter, shut the lid quickly, you kind of stir it around, and then you watch the temperature change that happens. So that's what the thermometer in there is for. So if you think about this, I've got a hot piece of metal going into probably like tap water temperature stuff in there. So if you think about what's physically happening, once I put that piece of metal into the calorimeter, remember the lid is on tight. If this water around here is room temperature and the temperature of my metal is boiling, okay, boiling water temperature, so 100 degrees Celsius, what's going to happen initially as we get going is that the energy is going to go out into the calorimeter. And what will happen is when you're doing an experiment, you will watch the temperature change and change until you hit a plateau. Now that could be an increase in temperature if you are looking at an exothermic process happening inside the cup, or a decrease in temperature if you're looking at something endothermic. Now in the case of this, because we have a hot piece of metal, it is going to be exothermic for that piece of metal. Okay, so when we do our calculation, it's really important that you keep the signs straight. Remember, the temperature of the metal is dropping. Okay, now what we are going to do to figure out information about this piece of metal here is look at what is going on with the water, because with the water should have gained whatever energy is coming out of this cylinder in equal number of joules, but in opposite sign. So if the metal has a negative joule value, then the water has a positive joule value. And when we do these experiments, the temperature, that plateau, is the same for the piece of metal and for the water. It's what we call thermal equilibrium. So when I pop a piece of metal in there, like I said, we're looking for a plateau. So in this case, you'll see a spike in the temperature of the water, and then eventually you hit a plateau. If we were observing the temperature of the metal, you'd see a drop, and then you would see a plateau, and they end at the same temperature. So it's kind of like you're looking for the change, and then when it hits that plateau, that is what you are looking for to find your delta T. Okay, so like I said, I think the math is going to be important here. I'm going to show you a problem that I honestly think is a little bit more complicated than you're going to see on the AP exam, but I want to show you how it works so that you can translate it into the situations you will see it on the AP exam. And we're going to look at those another day, but today we'll look at this because I think you have to look at these types of problems to have this make sense. So here is the big beefy example that you will not see on the test. The next one we're going to do, you definitely could see. So a piece of metal weighing 59.04 grams was heated to 100 degrees Celsius. So that could be that little cylinder we talked about. And then put into 100 milliliters of water, initially at 23.7. The metal and water are allowed to come to an equilibrium temperature determined to be 27.8 degrees Celsius. So that's that plateau they hit together. They both are 27.8 degrees Celsius. Assuming no heat loss to the environment, calculate the specific heat of the metal. So we are going to go to my .cam, trusty .cam as usual here. I've got problem number 1 written here. And like I said, I don't think they are going to give you a problem like this on the exam, but I think that understanding how all of this works is going to be important for understanding calorimetry when we talk about a chemical reaction, okay? So when we read through this problem and we're looking at stuff, we have information about our metal and we have information about our water. And in this case, I think even with chemicals, I like to draw a picture, but in this case, it's just a piece of metal. So, hey, look, there is a piece of metal. What we're going to do is think about what happens to it physically first. And the reason why is we need to determine what is negative Q and what is positive Q. So we've got a piece of metal. I'm going to make some lists here. I've got information for my metal and I have information for my water. So I'm going to make those lists as we go along too. So I have my metal, and the mass is 59.04 grams, okay? So I've got my metal's mass, and it was heated to 100 degrees Celsius. So that means my T initial is 100 degrees Celsius, and then put into 100 milliliters of water. Well, we know that if I have a mass of water and it's 100 grams, assuming the density is 1 gram per milliliter, I have 100 grams of water. And the water's initial temperature is going to be 23.7 degrees Celsius. Okay, so the metal and water were allowed to come to an equilibrium temperature. So we know that since this is colder, this guy here is hotter, it is going to drop in temperature. So my T final is going to be 27.8 degrees Celsius. And my T final for my water also is going to be 27.8 degrees Celsius. So we've got both of those pieces of information the same here. Now, if we think about our equation MC delta T, I'm looking for the specific heat of my metal, so I don't know what that is, but water, and this is why we need to know this one by memory, is 4.18 joules per gram degree Celsius. So I need to know that one. And when you think about this situation, we have the heat going out of our metal because the temperature is dropping. So our metal is going to be the negative Q and our water is going to be the positive Q. So the metal's losing the heat, the water is gaining the heat, okay? So you have enough information here, M and C and delta T, to figure out how much energy the water gained. So we're gonna do that first. We have the Q for water equaling M times C times delta T. So it's 100 grams times our specific heat of 4.18 joules per gram degree Celsius times our delta T, which is going to be, remember, final minus initial, 27.8 degrees Celsius minus 23.7 degrees Celsius. All right, so we have our temperature change here. And when we put all of these things into our calculator, you should get a Q value of 1,713.8 joules. So what this means is that I gained, for my water, 1,713.8 joules. So out here, I had a plus 1,713.8. That means that the water must have given me all of those joules. So now what it helps me do is, if you think about this equation right now, we currently kind of have two variables. We don't know what the specific heat is, but we also don't know how much energy the metal lost. Now we do, because we use the water as the mirror to figure that out. And so here is what's important. If the water gained 1,713.8 joules, if I want to figure out my metal now, okay, the Q for my metal is going to be negative 1,713.8 joules. So it's negative. So if the Q for my water is positive, this is negative. And the signs are really important here in terms of being able to get points on the exam. So you really have to be careful with how you put those signs on there. So in this case, the negative value is equal to MC delta T. And you know I like to solve this first. I probably shouldn't have put this in here, but it would have ruined the dramatic effect. So I'm looking for specific heat. So I'm going to divide both sides by M and delta T. Okay, so my specific heat is going to be the negative 1,713.8 joules divided by the mass of my metal, which was 59.04 grams. And then my delta T here is going to be, my final temperature was 27.8 degrees Celsius. And then I'm subtracting it from 100. Okay, now this, because I'm taking 27.8 and subtracting 100, is going to give me a negative number. And that's important because now I'm going to have my negative cancel out a negative and everything's going to be right in the world. Be careful, like I said, when you put this into your calculator, make sure that this is realistically in parentheses here so that I can put that in and get order of operations correct. So when I put this into my calculator and I solve, I'm going to do negative 1,713.8 divided by these two numbers here, and then I end up getting a specific heat of 0.402 joules per gram degree Celsius. So like I said, we can use what happens in the water to figure out what's going on in the metal, because I cannot stick a thermometer into a solid piece of metal. It's not happening, but I can use the water as a proxy to make that happen. So like I said, I think this is a little more complicated than what you are actually going to see on the exam. On the exam, you are going to see probably one of two things. Either they're going to give you all the information for the water and you're going to have to figure out the Q for a chemical. And if there's a chemical, which we will get into in our next lesson, this part is kind of a moot point. The other thing they could do is they could give you this energy value here already and ask you to figure out the information without making you do both of these calculations. So I have seen it, like I said, where you do kind of one half of this table, but I want you to kind of see how this works on its own. And what I mean by that is we'll take a look at a second example so you can see what I'm talking about here. Hopefully this isn't too confusing so far. Okay, so here's example 2. This I feel like is a possibility of something you could see on the test. So we've got 25 grams of mercury heated from 25 degrees Celsius to 155, and it's telling you it's absorbing 455 joules of heat in the process. Calculate the specific heat capacity of mercury. So when we look at this problem, they are already telling you how many joules went into that. Now that probably happened through a calorimetry process, but they're telling you that energy value. The other thing and like I said, we'll get into this in a little, in the next lesson after this, I could give you all the information for water, and then we're implying that that is happening because of a chemical reaction. So it's, you know, one of those things, you gotta deal with semantics here a little bit. So we'll work example 2, and then I'm going to give you some time to take a look at a simulation, and then we'll be good to go. So 25 grams of mercury heated from blah, blah, blah. We've got 450 joules. So we've only got one substance here, and it's just mercury. So information we do have, we know its mass is 25 grams. We know that its T initial is 25 degrees Celsius and its T final is 155 degrees Celsius, right? So we know its final temperature and its initial. We also know the heat that made that happen was 455 joules. So like in our previous problem, we had to figure all that out with the water. They're just giving that to you already. So this is a little bit easier. So now it's just finding our specific heat. It's the, variable that we're looking for. So we know Q equals M C delta T. We're looking for C here. So I'm going to divide both sides by M delta T. And you might say to yourself, this is getting kind of repetitive, but I need you to see all of them. So my specific heat is equal to Q divided by M delta T, right? So it is 455 joules worth of energy. Now, the signage thing is a little bit weird here because it's telling you it's heated, but let's look at our delta T to see if we can kind of figure this out. So our delta T is going to be 155 minus 25 degrees Celsius. So that's going to give me a delta T of 130, which is positive. That means I don't have to turn this sign to a negative because it's just telling me that I absorbed those 455 joules, right? And the sign makes sense with the energy, so we should be good to go. But you got to watch that sign because you could get a negative specific heat, which isn't physically possible. So 455 joules, my mass is 25 grams. And my delta T is 130 degrees Celsius. So when I put those into my calculator, I'm going to put parentheses around my denominator to make sure everything works out okay. And I will get a specific heat of 0.14 joules per gram degrees Celsius, right? Feel okay about that, hopefully, because there's nothing super crazy. Now, one thing I want to tell you about is that with a couple number tweaks, this could actually be a decent multiple choice question. And you say to yourself, aren't we done with these practice problems? Yes, but I want to show you something. So let's say they give you 455 joules, but instead of 25 grams, let's say our problem is a 45 gram sample, okay? And let's say it had a delta T, not of 130, but 100 degrees Celsius, okay? So if we think about reworking this, it would be 455 joules over 45 grams times 100 degrees Celsius. Now, when you think about this, that means that if you do the mental math, remember on the multiple choice test, we don't get the calculator. So we'd have 455 joules, and then 45 times 100 is 4,500. So we'd have about 450 divided by 4,500. And so that gives me approximately 0.1. So there's kind of some, I call it estimation math, where you got to do a little bit of mental math and kind of figure out those numbers, but they're going to give them to you in nice ratios. All right, it's kind of a lot to digest. We are going to take a look at a simulation next. Then we're going to talk about chemical reactions. Then we're going to talk about dissolving, or vice versa. I'm not 100% sure of which one we're going to do first, but we're going to talk about chemical processes in calorimetry next after we look at our simulation. So if you find yourself having any questions, please make sure you get them cleared up. Otherwise, good luck.